Good morning, everyone. My name is Maasoumi. I'm delighted to welcome an old friend and a distinguished econometrician, Whitney Newey, to this keynote address for the International Iranian Economic Association. Whitney is a very busy man, as you might suspect, and I'm really grateful that he's agreed to make this timely presentation to our association. Just a few highlights about Whitney to introduce him to the younger members of our association and some students around the world. Whitney is the Ford Professor of Economics at MIT. He's a distinguished fellow of American Economic Association, a fellow of Econometric Society. He even was the editor of Econometrica and, believe it or not, also chaired the department at MIT, which tells you what a nice and effective person he is. In fact, Whitney is universally respected for his craft and his contributions, which range truly widely. Every major topic of concern either begins with his ideas or takes off with some impactful contribution by him and his co-authors and his students. Whitney is also universally well liked because he really believes in serving the economics and the scholarly community. And as I'll explain, is a theme, the theme that I pick to highlight in terms of his work and topics. Whitney, because I'm old, I can remember, wrote his PhD with Jerry Hausman, an old friend. And Jerry has had some really fantastic students, including the late Hal White and Ben Bernanke. But Whitney now perhaps surpasses that. I'd like to know what Jerry thinks about it with the students like Josh Angrist, who just won the Nobel Prize in Economics, and Isaiah Andrews, who won the Bates Medal in Economics, and many, many others. The theme that I want to pick to emphasize in Whitney's work is then a scholar who looks at what social scientists need to do rigorous learning from evidence, and then rigorous statements about what we learn. And what he does is comes in and looks at the issues in the greatest generality possible, and produces results that are accessible and allow rigorous inference in a very difficult observational data environment. The examples I could cite in that regard are famously the Newey West hack estimation, robust estimation of the standard errors. Economists are challenged by heterogeneity and what is left unexplained by the residuals in their models. And to model these unknowns is difficult because presumably we don't know much about these errors. And yet to be able to report robustly what is the consequence for uncertainty of our findings is something that economists are challenged with. And Whitney and West paper, tens of thousands of citations, produces very accessible methodology and code to do that. And so that's just an example. When he writes even introductory and explanatory chapters, like the one he wrote with on asymptotic theory with Mike Fadden as a go-to piece, other than the books by Hal White, for generations of economists to go to that chapter in Handbook of Econometrics to learn how to do econometrics rigorously in the most general settings that we need to deal with in econometrics. The current topic, again, to put it in that same vein, that perspective, is dealing with the two fundamental challenges of econometrics, what functional form and what covariates to put in a model. These are the two challenges that almost every problem in econometrics can be translated into meeting those challenges. Economic and social theories are not very helpful in terms of what functional form. And given that we lack the ideal experiment, we don't know what covariates to control for. So big data's big promise is to deal with those. Machine learners can be very, very general, and they predict frighteningly well. The ultimate challenge of predicting well is met, but we are now dealing with a sort of a black box with big data machine learners. And so try to get us back to analyzing a policy and make optimal decisions, discover partial effects. What big data people call causal analysis requires a rigorous discovery of partial effects of the covariates in these models. And machine learners famously or infamously do very badly in that regard, even though they predict well. They're not very good at telling us what the causes are. So this really exciting development in terms of double machine learning and now debiased and automated ways of dealing with very general settings in which you can actually find fantastically debiased estimates of partial effects is what excites me. It sort of brings back econometrics into the middle of big data and lets us go back and do what we want to do, policy analysis. So I was excited that to see this work at a joint keynote presentation in Paris, I guess a couple of years ago in the middle of COVID. And since then, I've been writing about it excitedly, telling people excitedly, and I've used some of the methodology that Whitney is going to talk about in the context of portfolio analysis. So I am truly pleased that Whitney has agreed to share the developments and the possibilities in this area with our wonderful association. And I think Whitney is going to go for about an hour until 10 to 11. And then we have about 10 minutes of Q&A before we let him go to deal with this multitude of other burdens. Whitney, welcome to our association, and thank you for being here.
Well, thank you. This is a very kind and generous introduction, and very interesting too. I think explained really well my reasons for the enthusiasm in this as well, to try and use the modern tool we have, see effects and other interesting economic things. So that's wonderful, wonderful. Can you see my slides at this point?
Not yet.
Can you see my slides?
I can't. Maybe
okay,
it has
so I need to go share. Right, let me go share
yeah.
them. We have. Okay, I'll share. Let me do that. Just a minute. Share. There they are.
There may be some issue with
okay.
the audio.
Now?
Yeah, I can see this.
Can you? Okay, you can see them now.
Yeah, I can see your slides. But there's some issue with your audio and video. I can't see you anymore.
Can you hear me?
I can hear you now. Yes.
Whitney, might be better if you turn your camera off, perhaps. Maybe there's
and I can see you as well. I think we are good to go.
Okay. 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 Very good. This is in words, recap what Essie just said. Many interesting objects depend on a regression or other first step. OLS regression with many covariates, IV regression with many covariates, where we're interested in one of the coefficients in both cases. Average treatment effect depends on an average outcome given covariates and treatment, or the propensity score, which is another regression that enters the thing we're interested in. And then there are structural economic models that have similar features, like a discrete dynamic structural economic model, often written down to depend on conditional choice probabilities. Hodson-Miller formulated things that way, and so that's another example. And then other things too. The regression or other first step may be high dimensional. There might be many covariates, for example. And as Essie said, machine learning provides good prediction with many regressors. Amazing, really, how well machine learning can do at prediction. And in different settings, people use lasso, neural nets, random forests, and other things. And these have these amazing prediction properties. One of the things, though, that one of their features is they're biased. Just the inherent nature of trying to do prediction in a high-dimensional setting involves some kind of regularization or model selection somewhere. And what that does is that introduces bias. Okay, so let me see how I go to the next. There we go. For example, lasso, to get the good performance that you get with lasso, you penalize the sum of squared residuals by the size of the absolute value of the regression coefficients, and that introduces bias. That penalization introduces bias. So and then what happens is if you take that machine learner and plug it into a formula for a parameter of interest, the regularization bias just passes right through to the parameter you're interested in, and it gives poorly centered confidence intervals for the parameter of interest. Really bad, actually, and for a lot of these. And something similar happens with model selection. If you might say, well, I'm not doing regularization, I'm doing model selection, so am I okay? And the answer is really no. With model selection, then local mistakes under root-n alternatives lead to invalidance intervals. And it's still a shift, it's a bias that gets introduced, and so it doesn't work. A solution to both of those kind of biases, the regularization and model selection biases, are named or functions for GMM. Okay, so that's the solution. Is name and orthogonal moment functions for GMM. And what we mean by orthogonality, it's a little bit of a funny name for this, but I'll explain more about that a little later. Orthogonality means that the first step, whatever your machine learner is, has no effect the first order on the average moment function. If you will, the derivative of the moment function with respect to the first step is 0. Now, we also do something else along with these orthogonal moment functions. We use something called cross-fitting, which reduces overfitting bias and allows for complicated machine learning first steps as well. Okay, so so I'm going to talk about these orthogonal moment functions a little bit, just a little bit, and give some nice examples of them. Something that we're familiar with. Sorry. And hopefully this will be useful to you. So that's one of the goals. I want to introduce this, and I'll come back to that. So that's going to be the primary example. Okay. So for an introduction to this whole effort that we've been working on, there's this paper in Econometrics Journal. it's written in kind of an introductory style. Okay, so that's good. Theory given there's theory given in this paper when it's Emory and Robbins in econometrica, and then we introduced an automatic debiasing method in this paper with Victor and a student Rahul Singh. And the neat thing about that is you only need to know the moment functions to construct the estimators. You can do the debiasing using the moment functions themselves, and don't need to know kind of the formulas for the debiasing. Okay, so that's useful. Unfortunately, it's hours short. I don't want to get too far away from the basics in an hour, so I'm just going to refer to this. You can do this. It's great. It's kind of the natural extension of what I'm going to talk about to much more complicated settings. There's many more recent papers. It's not the only thing that I do, but it's occupied a lot of my attention the last few years. There's a handbook of econometrics chapter under development, and hopefully that'll be ready in a few months. So today, what I thought we could do is work through some introductory notes from the first year graduate econometrics sequence at MIT. But it is in the first year, and it's pretty straightforward and easy to use. And so I thought it'll, in terms of providing something useful, hopefully this will be useful to you. You can use it, when you're running a regression with many covariates, you can use this immediately. And the evidence so far is it works really well. Okay, so that's what we're going to talk about. Okay, so let's see. You probably can't. Let me get right. Okay, so we are. Can you see that, or is the screen sharing thing blocking it? Let me
No,
move that.
we can see it.
Okay, so it's just blocking it. So we're going to consider GMM estimation where theta is the main target. Okay, so that's going to be our parameter of interest, our policy effect, a causal effect. And then we're going to have other very high dimensional nuisance parameters, eta. And we're going to assume that those can be identified and estimated without knowing theta. Okay, so they come from somewhere else. It could be a could be the others of some kind. Okay. So,
Whitney, you might consider turning your video off, your camera, to see if it can get a better bandwidth so that it doesn't interfere with the audio.
Yeah, if I can, okay. Let me try that. Okay, so it's going to take a minute. Let me see. How do I do that? Let me try stop sharing. Let me try stop sharing for just a minute. I'll turn off the video. If I turn off the video, I'm sorry.
So you see in your menu you have a camera.
Okay.
And
stop video.
I can.
Exactly. And then now you can share back.
Okay.
I wonder if it helps.
Is that working?
Yes.
There we go.
Yes. So just share your slide.
Okay. Okay. Great.
Perfect.
Okay. So we do this debiased GMM setting. Okay. Did I lose you?
No, I'm here, but I just try to help with all the bandwidth by turning off my camera.
Okay, got it. Okay, so Okay, so this GMM setting here is not the most general one, but it's a very practical one, common one that we often look at and use. And as we've talked about, if you think about using a preliminary estimate of the nuisance parameters, which is a high-dimensional modern machine learner such as Lasso, generally it does have a spillover effect on the estimation of the main parameter, and we'll see that. In general, there is a spillover effect, and it poses difficulties for inference about theta. We eliminate the spillover by working with scores or moment functions that have this name and orthogonal structure, okay? So that's what we're going to do. And in fact, one way to get this name and orthogonal structure in regression models is to partial out the covariance. So if you have what you have is you have a regression, a lot of covariance, along with some effect you're interested in. The partialing out, where you take residuals from a couple of other regressions that we're familiar with from regression estimation, is actually creating an orthogonal score. And so that for regression, this parceling out is, it really solves the problem. Okay. So, and we'll talk about that. Okay. So parse can be used to estimate regression parameters of interest, like an average treatment effect, in the presence of high-dimensional nuisance parameters like covariance. And it produces moments that have this orthogonality structure. This orthogonality turns out to be the most crucial property where nuisance parameters are high-dimensional. And so the high dimensionality of the nuisance parameter necessitates the use of some kind of regularization or model selection. And so in that setting where you're doing high dimensional estimation, orthogonality is just a very crucial property that helps us. Here we're going to outline a general debiased GMM approach that provides high quality estimation and inference of theta based on the use of orthogonal scores. And we just want to go on actually from that. Okay, so let's start with something we all know for applied work is just linear regression with many controls. Okay, so consider a regression model. You have a outcome variable y of some kind, and then you have a target regressor. You think of this as treatment. D, it's often used in notation for a treatment dummy, for example. And then the parameter of interest is going to be theta. D could be a policy variable as well. So again, interested in the effect of some policy on y. And the parameter of interest then is alpha. And then the W's, those represents P controls, where P can be large and not small compared to the available sample size. Okay, so P is the number of controls, and this can be large. So we're interested in alpha, but we have these controls that we need to put in the regression in order to get rid of omitted variable bias, the classic regression way to say it. Or you could think about conditioning on covariance so that you can interpret alpha as a treatment effect. Okay, so let me go back. Oops, sorry. Sorry about that. Go back. Okay, apologies. Get this down. All right, let me try using just the arrow. There we go. Okay, so what do we do when we partial out? What we do is we take a residual from regress. That's going to be y tilde is going to be this residual. And from regressing y on the covariance, and we take a residual from regressing d on the covariance, and that's going to be the d tilde. Okay, so we take these residuals, and then we just look at a regression of the y residuals on the d residuals. Okay, and that is going to create this orthogonal moment function, okay, or orthogonal score. So here's the definition of d tilde. D tilde is the residual from the population regression here. This is the population regression of d on the covariance w. Okay, and that gives us d tilde. These are the coefficients of that population regression. Okay, y tilde is the same thing for y. It's just y minus the coefficients of a population regression of y on w, which you get by minimizing the expected squared residual. Okay, and so what we do when we partial out is we take the y residuals and we regress them on the d residuals, and that gives you the coefficient of interest, this alpha. Okay, so okay, that produces moments that have this orthogonality structure. Okay, and we did this already, sorry. Okay, the part you can think of then the alpha is gotten from just this simple regression of y on d after parceling out the w's. Okay, and here's the standard regression formula for a univariate regression of y tilde on d tilde. Okay, got the second moment of d tilde inverse times the cross moment of d tilde with y. Also, the first order conditions for this are just solving a moment equation. So this becomes you can think of this solution alpha here, this regression, you can think of it as GMM as usual, where you just have this as your moment function. Okay. And this is the first raw level parceling out. Now we're going to consider estimation of alpha in a high dimensional setting. And for estimation purposes, we'll assume that we have a random sample. We'll mimic in a high dimensional way the parceling out procedure in the population. Okay. Now, when P over N was small, we know what to do from classical econometrics, right? You just run a least squares regression in the data to get a data version of y tilde. Oops, sorry. And then you do the same thing for D to get a D tilde in the sample, and then you just regress the Y residual on the D residual in the sample. Okay. When Pn is not small, we employ instead a lasso in the parceling out steps. And so we do the parceling out using lasso, and we can summarize that as this procedure. Okay, so this is what we might call double lasso. We run a lasso regression of y on wi and di on wi. So the first one, the first line of this equation, or the first equation, that's the lasso regression. Okay, you minimize this objective function, the sum of squared residuals, plus lambda 1 times the sum of the absolute value of the coefficients. Okay, and there's this lambda that you have to pick. When you do this, you can just do it by cross-validation. And like R has code that you can use. There's a standard procedure program in R you can call that will do this for you. There's other things you have to do. You have to get the scale of these W's all to be the same. And R does that for you. And then it'll pick lambda for you by cross-validation. Okay, so just think of this. These are the coefficients of an R program, right? Which you get from a regression of Y, lasso regression of Y on W, where you pick lambda by cross-validation. And that's fine. Okay, and then you have similarly the lasso coefficients from the regression of D on W, lasso regression. And then you take the residuals from those. You just take, the Y residual, Y tilde, as it were, or twibble. Okay, is yi minus the coefficients times the w's, and then you have the d residuals. Okay, and so you take these lasso residuals, and then you just regress the y residuals on the d residuals, or not all this moment equation. Okay, that's just the normal equations for the least squares regression of y on d. Once we've done that, this is an orthogonal. This is the orthogonal moment equation right here. By this partialing out, you've created what is an orthogonal moment equation. Okay. Okay, and so you do this, you do lasso, get y residuals, you take the lasso regression of y on w to get lasso residuals, you take the lasso regression of d on w to get d lasso, and then you just regress the y lasso residuals on the d lasso residuals. You solve this equation, and that's debiased machine learning estimate of the coefficient of alpha, the coefficient of interest in that regression. Okay, and we call it double lasso, or you can call it double lasso if you want. You run lasso twice to parcel out the covariance out of the regression. You run lasso twice, do a y lasso regression and a d lasso regression, and then you just regress the y residuals on the d residuals. Okay, so that is, let me pause there. Are there any questions? Oops, sorry. My arrow down arrow is not working. So, oh, there, now it is. Okay. Any questions? Okay. All right. So, okay, so a little theory. You can show that this works. You need some regularity conditions. One of the regularity conditions is that, and it's actually sort of a feasibility condition for this. It's not just a regularity condition, is that the coefficients have to be small enough. There can be, it doesn't have to be sparse. You don't have to have a lot of the coefficients in those two regressions, the regression of y on w and d on w. Those don't have to have a lot of zeros there, but they do have to be, small in some sense. Absolutely summable is one condition that's implied by this one, actually. That the coefficients, if you sum them all up, take their absolute values and sum them all up from j equals 1 to infinity, that they're small. I mean, that sum is finite. Okay, that's one condition that is a little weaker than this. And this is just meant as one kind of version of this, that what this says is that for some ordering of the coefficients, could be different for the y regression and then the d regression. For some, there's some way to reorder all of these coefficients so that they satisfy this inequality. And the thing that's sort of nice about this theoretically is you don't have to know what the reordering is. You can run lasso regression without knowing which are the big coefficients. Lasso regression will pick those out for you, as it were. And so that's the really nice feature of lasso. And then with some other regularity conditions, you get asymptotic normality, root n theta twiddle minus, alpha twiddle minus alpha will be approximately distributed as a normal 0D. Okay. And this will be the asymptotic variance, the standard white asymptotic variance, and you can estimate it by just using the usual estimate of a heteroscedasticity consistent, using the usual construction of an heteroscedasticity consistent variance estimate. Intervals in the usual way, just like in the low dimensional case. Okay, and then the standard error, as we said, this is just the white estimate of the asymptotic variance, and then a confidence interval could be constructed in the usual way. 95%, confidence interval would be just your estimate minus twice the standard error, or 1.96 to be precise. Okay, any questions about that? Okay, so run lasso, right? You run lasso on y on the covariance, lasso of d on the covariance, and then you run the y residuals, just do ordinary least squares of the y residuals on the d residuals, and use the white standard errors from that regression of the Y residuals on the D residuals, and you can just do standard inference using that. Any questions anybody has?
Whitney, one quick question. In terms of reporting
Sure.
economic results, this alpha would be the partial effect of D on Y. We typically say given the number of years of experience, or parental income, or the other W's, right? Here by lasso, the two regressions, the two lassos may or may not get the same W's, right?
That's right. And yeah, no, that's right. Absolutely. And in fact, it's essential for the debiasing that they not be forced to get the same W's, actually, because you may have in the D regression, you may have a W that's important that's not in the Y regression, and
That's right.
And that helps with biasing. So that's a good point. Thanks for pointing that out.
I guess what one could do is say the alpha is the partial effect,
okay,
the treatment effect, given the total set of W's, the joint distribution, the distribution given all the W's that were ultimately selected. That could be one reference
about it. And
yeah.
You could even think of it as the potential W's, and the remarkable thing about lasso is you don't need to know which W's are important, right? That's the remarkable thing about lasso.
Yes.
So,
thank you.
So somebody raised their hand. Ariane Manafi Nayazi. Happy to answer a question.
Let's see if Kamia can enable them to
Thank
answer.
you. I just have a question about the functional form of the W here. Here, the setting is completely linear, but let's say we don't know how the control variables are related to each other. So
we're getting there.
Hello?
Go ahead.
Okay.
Go ahead, I can hear you.
Yeah, but when we don't know the functional form of the W, can lasso works still consistently here? Thank you.
Great. That's a really great and fundamental question. You can allow for nonlinearities by putting in nonlinear functions, but as a non-parametric method, lasso is a bit limited in scope. Shouldn't go into it in detail. Because the regular conditions that are required, you might use some other machine learning method, like to do the parceling out. If you're really worried about nonlinearities, maybe you should do it by neural nets, the parceling out. Instead of doing lasso regression of Y on D and Y on W, sorry, and D on W, do a neural net regression if you're worried about nonlinearities. If lasso is really designed more for the covariate case, where there's just a set of covariates rather than a non-parametric parceling out. So that's a great question, actually. That's a really good question and good thing to be aware of. The one thing to know is, the one thing I want to emphasize is that you can use any machine learning method to parcel out. That
Thank you.
always created. Go ahead.
I'll say thank you.
Okay, very good. Okay. All right, good. All right. So I'm going to empirical application. How are we doing on time? That's good. Okay, so
20 minutes.
Growth theory. What? No,
20 minutes.
Okay, thank you. Classic growth regression in that we're familiar with, you know, in macroeconomics. It's not a lot of active work currently, but this is a classic regression. We're interested in how economic growth rates, Y, are related to the initial wealth levels in each country, controlling for countries' institutional, educational, and other similar characteristics, W. Okay, so here's the regression. So this is growth rate. This is initial wealth level. And here are covariates. The relationship is captured by alpha, and that's a speed of convergence divergence, which predicts the speed at which poor countries catch up when alpha is less than 0 or fall behind when alpha is greater than 0. So the catch up happens if alpha is less than 0. That means the higher your initial wealth level, the lower your growth rate. And that's the convergence hypothesis. Really, the convergence hypothesis is that alpha is less than 0. Empirical question is, do poor countries grow faster than rich countries, controlling for educational and other characteristics? In other words, is the speed of convergence negative? This is the convergence hypothesis predicted by several growth models, including the classic Solow model. And this regression can be given a causal interpretation under some strong assumptions. So we're not going to state that. We're going to just do the regression using the outcome, realized annual growth rate of a country's wealth, gross domestic product per capita. The target regressor is the initial level of the country's wealth. The target parameter is the speed of convergence, which measures the speed at which poor countries catch up with rich countries. We have a lot of controls in that, you know, classic data set, measures of educational level, quality of institution, trade openness, political stability in the country. And the sample that, again, the classic sample, this is what classic sample? Well, this is from Barrow and Salamartine. Okay, I don't know if I pronounced the last one right, but the classic, you know, paper on this. Okay, and there were 90 countries in the sample after, you know, deleting some missing observations, and about 60 controls. Okay, so what we're going to do is do the double lasso on this and compare it with just putting in all 60 controls. Okay, so here P is about 60. You have 60 potential covariates. N is 90, and P over N we would say is not small. I have, you know, 2/3 as many regressors as the sample size. So we expect, actually, in that case, least squares to provide a noisy estimate of alpha. And we expect that a method based on parsing out with lasso to provide a high quality estimate of alpha. Okay, so what do we get? We just run OLS on all 60 controls. You get, it's a negative estimate. It is negative, but it's not significant, you know, at any reasonable choice of size. And so, on the other hand, when you run double lasso, you get an estimate of minus 0.05, so it is negative, and quite a much smaller standard error, a standard error that's less than half as small. And so it is, and it does become significant. Least squares provides a rather noisy estimate of the speed of convergence and does not allow us to answer the question about the convergence hypothesis. Sharp contrast, double lasso provides a more precise estimate. And there's the point estimate about minus 5%. And the 95% confidence interval is minus 7.8% to minus 2.2%, which does not include 0. So it's significant at the, you know, 5% level. Okay, so it does, so to speak, support the convergence hypothesis. Okay, any questions about that application or anything else? Okay, so that's okay. So why? So why does this produce, how does it work? Well, because it produces orthogonal estimating equation, and we can check that. A little bit of this name and orthogonality property. Okay, so here the nuisance parameters are these coefficients. Okay, we're going to formulate it that way for this purpose. The nuisance parameters here are these coefficients. Okay, in the parceling out regression for y and for gamma, and there's a lot of them, right? So there would be in that application, how many would you have? You'd have 60 covariates, so you'd have 120 of these parameters. Okay, so there's a lot of them. Now note that double lasso exploits the empirical analog of the following moment equation, moment condition. Okay, so A is the parameter of interest, A is the nuisance parameters, and here's the moment condition that you're solving to get to alpha. Okay, the true value, alpha, solves this equation when eta is equal to these regression coefficients from the regression of d on w and from the regression of y on w. The y tilde again denotes the residual, and we're going to let it depend on eta. And now we're allowing this to depend on eta, this eta to be anything, right? So this is the 0, that's the true coefficient, and when you're at the true coefficient, you're solving this to get alpha. What we want to do though is look at name and orthogonality. We're going to want to look at, the effect of eta on this and show it 0. Okay, that's going to be the name and orthogonality. And so for that purpose, we want to allow these eta 1 and eta 2 to vary. Okay, the true residualized quantities correspond to eta equal eta 0, right? Which is right here, right? So these are the true residuals. Here, the eta, y tilde and the d tilde are the true y and d residuals. Just as a function of just a moment functions right here. For the scores as a function of these etas are just these things, okay? All right, so that's the setup. Now it's straightforward to show that if you take the derivative of g with respect to eta, evaluated at the true alpha, it's gonna be 0. Okay, so now how do we see that? Well, let's go back and look at this. So here it is right here. Let's see, let's do the easiest one first. Okay, so in fact, maybe we'll just do the easiest one. Look, if we take the derivative of this with respect to eta 1, so we're going to take the derivative of this with respect to eta 1, okay, and here's the expression for the residual right here. So we'll take the derivative of this with respect to eta 1, what do you get? Well, you just get a minus w here, right? And over here, so you get a minus w is going to come in here, and then, we're holding eta 2 fixed at its true value. So by the chain rule, you take the derivative here, that'll be multiplied by this. This is the residual from the projection of d on w. That's orthogonal to w, right? And so right here, you get minus w, right, times the residual from the regression of d on w, right? Right, pull the minus outside, there's the residual from the regression of d on w, and that's 0 because in the population, the covariates are orthogonal to the regression residual, okay? The other one, it's got 2 terms, but you have the same thing there. There's two orthogonality conditions like that, one for the y residual and one for the d residual, give you expectation. The derivative of the expectation of the moment function with respect to eta 1 is 0. The derivative of the expectation of the moment function with respect to eta 2 is also 0. Sorry. Okay, so that says that to first order, these etas have no effect the expectation of this moment function. The moment condition is formulated in such a way that small perturbations in terms of biased estimation of these parameters will translate to a negligible effect on estimating the target parameter. Okay. And so in high-dimensional problems, we estimate the nuisance parameters through solving prediction problems where we have to regularize in order to do these predictions, which results in biases. The actual estimates of the etas are going to be biased. But name and orthogonality assures that these biases do not transmit to the estimation of the target parameter to first order. Okay, and one by one. We're taking partial derivative with respect to eta 1, partial derivative with respect to eta 2. So, to first order, each of eta 1 and eta 2 has no effect on the moment function. And that gets rid of the first order effect of this bias. And that's enough to get root inconsistency and asymptotic normality. And in practice, that's enough to reduce the bias, to get rid of, in lots of Monte Carlo, that gets rid of nearly all the bias. Okay. All right. Any questions about that? Okay. Okay, how are we doing? We're down to about 10 minutes, right?
Yep.
Okay, so you have, by parceling out, you get a name and orthogonal moment function for regression with covariance. Okay. There's another way you can think about it, that the alpha itself is first order insensitive to the local perturbations. Okay, so you can think of as a function of eta, when you do parceling out, you're getting an alpha that depends on eta. And in fact, the derivative of that alpha, the derivative of that alpha with respect to eta is going to be 0. And how do you get that? You just use the implicit function theorem. The derivative of alpha with respect to eta is just this, right? And so we already showed that this was 0. So one way to think about name and orthogonality, another way to think about it is the effect of the nuisance function on the parameter of interest is 0. Its derivative is 0. Okay. That's how you can think of generalizing this beyond GMM. Okay, so that's the purpose of doing that. Okay. Now, let's see what happens if we don't do that. Okay. Okay, so let's see what happens if we don't do that. Let me go back and make sure that I got. Okay, what happens if we don't have name and orthogonality? Well, that's bad. Okay. If we don't have name and orthogonality, we should not expect to get high quality estimates of the target parameters. And if we don't, an example, of something that people have done is still used sometimes is a naive method where you do single selection. In this invalid method, one would apply lasso regression of y on D and W to select relevant covariates. Okay, you can do this. You can take a lasso regression of y on D and W to select relevant covariates, in addition to the covariate of interest, then just run least squares of y on D and the covariates you've selected. That doesn't work. Actually, this is a post-lasso estimation where we include D in the second regression. And despite its wide use and proliferation, this is not a valid approach to perform inference on alpha. Okay, and it can lead to very misleading conclusions. Here is a graph. Let me give you And let me give you that. Okay, so this approach, what's happening, if we think about it in terms of the moment condition, if we think about it, we're not parceling out, so we're just using, we're thinking of solving this moment condition for A and B, and this, we do not have name and orthogonality here. The derivative of this with respect to B, the nuisance function, the derivative of this moment function with respect to B, the nuisance functions is not zero. If D is correlated with X, it's not zero, right? Or if the expectation of D times X is not zero, then this is not zero. Okay, and so it doesn't have the name and orthogonality property, and it has large bias. For lasso, the bias will be of size approximately log P over N. And if you think about P growing with the sample size, which is what we typically think about when we do lasso, then it grows slower than 1 over root N, and that's bad. In fact, what happens is the confidence intervals shift away, the asymptotic ones shift away from the center towards infinity. The asymptotic coverage is 0 if you do this, actually. You can prove that. This estimator is not root N consistent. In fact, root N alpha hat alpha minus alpha has a bias constant that goes to minus infinity or plus infinity as N grows. And what that does is you get 0 coverage asymptotically. Okay, so that's bad. Now you can actually see it in a graph of a Monte Carlo. Here it is. So this is the double lasso here in the design, which is, I'm going to skip the describing the design, sorry. Standard design, you know, the coefficients vanish faster than 1 over j. It's like vanish like 1 over j squared. This is the double lasso. This is what we said, where you just, what we talked about, where you just do lasso regression to estimate the one coefficient, and you can see how biased it is. Okay. That's actually, so yeah, anyway. So not using an orthogonal moment function here leads to big mistakes. Okay. And this, you know, think about this as, take a 95% interval of this, it's close to not including the 0. 0, think of the true coefficient being 0 just in the Monte Carlo design here. This one's reasonably centered around 0, double lasso. This one is not, it's shifted a lot, and that's because you haven't done the parceling out. Okay. All right. Back one. The histogram naive estimator heavily biased. Orthogonal estimator based on parsing out is approximately unbiased and approximately Gaussian. Naive estimator doesn't perform well. And if you do these two, it's worth the effort to do these two prediction problems. You know, regress Y on W and D on W and take the residuals. The resulting residuals are approximately deconfounded. They need, solves two prediction problems, and that's what you need to do to an orthogonal moment function. Okay. Any questions about that? And how much time do we have left? Got a couple of minutes.
About a few minutes, yes.
Yeah. Okay, so let me just say, there is a general way to do this. I'm not going to, let's just say there is a general construction that starts from an identifying moment function and gets you an orthogonal one. Okay. In the case of a regression, it's the parceling out, which is very simple and nice. There are other, in other settings, you do other things. Okay. In IB, if you're doing instrumental variables, you can do parceling out again. You can parcel out the covariates out of the instrument, out of the left-hand side variable, and out of the right-hand side variable, and that works fine. But beyond that, it's a little more complicated. Just refer you to the locally robust paper. It talks about a whole bunch of these, lots of different, it gives a general construction, and I'm just going to not attempt to describe that here. This gives you something that you can, go and apply right now. You can, if you're running a regression, you have a lot of potential covariates. You can do double lasso, and it works fine. Okay, and let's see. I think why don't I stop here to see if there are any questions? Let's just stop here for any questions you have. I can go on if people want to a little bit more, but let's just see if there's any questions. Anything you want to ask? Ariane. Another participant.
Okay.
Go on. Go
Thank
ahead,
you.
Ariane.
I just have I want to know your opinion, since it is a new way of estimation using machine learning techniques. So let's say we are under two new, and we want to just talk about when we are deviating from the truth. So let's say we are not adding all the true control variables in our regression. So as far as I understand from your math, that this method is really sensitive to the true alpha. So if we kind of deviate from the true alpha by just considering not the true control variables in our regression, since it is machine learning, if we add lots of covariates, it's going to take care of it, and it will be okay. But let's say we are not adding the true one into our covariates. So do you think it is possible to talk about the pseudo-true values and the asymptotic theory of these estimators around the pseudo-true values of the parameter of the interest?
That's a great question. Okay, that's a great question. So a lot of the initial work on debiased machine learning depended on having a true regression, actually. But let me just say the locally robust paper doesn't. The debiasing there is completely non-parametric. So in other words, what I'm saying is complete. It's completely non-parametric. And what I mean by that is whatever first step you're using, if you use the construction in the locally robust paper, it debiases. It depends on the first step. Okay, so that's the way it does that. The debiasing in the locally robust paper depends on the first step in a completely non-parametric way, so it debiases. Well, what's an example? You raised a great question about this, about the lasso versus a non-parametric method, right? So that's an example. If you use lasso regression, the debiasing that you're going to do using the locally robust paper is going to be a little different, okay, than if you use a non-parametric regression like neural nets. It's going to be a little different, actually, and it adjusts to that. It adjusts to the first step you're using. So there is a way to do it. It's in the locally robust paper, and what's going on in that is the bias adjustment you're using depends on the first step you're using. Like if it's a lasso first step, which you can think of lasso as a regression on a bunch of covariates, right? A non-parametric thing would be taking the conditional expectation, right? Those produce different debiasing terms in using a locally robust paper. Okay, so the place that this is explicitly worked through Victor and Rahul, we kind of talk about this there. So the debiasing Ariane, do you know the average treatment effect at all?
Yes.
Yes, okay. So in the average treatment effect, the debiasing is if you think the regression estimator is your identifying moment condition. So I'm gonna take the regression evaluated at treatment 1 and the covariates minus the regression function evaluated at treatment 0 and the covariates. If you do The non-parametric is completely non-parametric. Okay. Then you get the classic doubly robust estimating equation. Okay. If instead you do lasso as a regression, then the debiasing term actually is a little different. It still has the residual from the lasso regression, but what you multiply is the projection of the classic debiasing function on those regressors. Okay, and that does the debiasing, and that's completely non-parametric. So anyway, so that's more than you wanted to know. The answer to your question is yes. The locally robust paper does debiasing that's non-parametric, and the way it does that is the debiasing depends on the type of regression you're using. Okay.
Thank you so much.
Okay, so
I think the great generality of the range of applications that Arian's questions refer to is the strengths here.
So there was another question too, right?
I think Hashim had a question, maybe.
Yeah, I just can you hear me?
Perfect.
Yes.
Can you? Well, first one, thank you, Whitney, for agreeing to give this talk to the association. As he said, we are all appreciative of it. I remember Victor gave this talk USC about 6 years ago, so I was very impressed by it. Yeah, hi. I was very impressed by it by then. But the problem, I think there is a couple of ones. I mean, I'm sure it's not related to your talk, but I thought I raised them because your talk is very specifically targeted on this issue that you have developed such a nice results. And the thing is that I think the assumptions of independence across units or across what you had, I think it was there. I mean, the other one is lasso. I find that often is not robust to the tuning. I mean, the cross-validation, especially if the independence assumption is not valid, which often is not, the cross-validation becomes problematic. And then there is a second issue, which is basically people assume this W matrix, the W covariance that you had is always known and is given, although it's large, it maybe is still incomplete or wrong in some way. I mean, I don't wrong in the sense that if some of them are zero weight, I mean, lasso deal with it, but if they are missing covariate which have non-zero weight, still we have a misspecification issue. And finally, when you apply these ideas to the dynamic setting like you did in the growth convergence, the question is, what are the covariates which are somehow given that you're looking at a very long horizon? And then how do we interpret the rate of convergence to equilibrium, which is basically, what is it? Because I didn't understand the 5%. Is it mean takes 100 years to get converged? Does it take 50 years to get converged? And what is the standard error around that information, which more relevant to policymakers and individuals? I mean, those are just basically general comments, just to balance it, that somehow we don't get this impression that somehow there's manna from heaven and all these problems that we know in practice are there going to be solved. I just wanted to, it's not a directly at your work, but I thought some of
those are great questions. Sure. Yeah, no. So, okay. So the first, I remember the last two. Let me do those two first. So the one about the covariates, yeah, that's kind of a generic regression problem, right? I mean, it's like, yeah, if you don't have the right covariates, then you mess up for sure, right? Yeah. No, absolutely. And it doesn't, you're right. The thing that this does allow is to allow for you to try with many covariates. Now, there's an important assumption that in order to try with many covariates, you need this approximate sparsity condition. You need to, you have to be, a few that are especially important, and that is, that is there. You do need, it does, the lasso absolutely depends on that in order to have these kind of good properties we're talking about. But at least you can, you have the potential here to allow for many, right? And so I like that. I mean, I like that. But it does depend on the approximate sparsity assumption for sure. The last part, yeah, I agree with you. I mean, yeah, go ahead. Good. Yeah, so the last one, yeah, so those are kind of, again, it's kind of a question about what the covariates are. And the last one, I remember your first question too, and it's kind of a question about what the covariates there are. And I'm happy to leave that to people. I mean, it's important. I'm not trying to, I'm not trying to say it's not important. It is important. And in an application, it's really important to think about that because it really determines, what covariate you, in general, what covariates you put in determine what regression you get, what the coefficient is on the, some variable of interest, right? We're saying basically, I'm saying that a linear projection, right, will vary depending on what covariates you put in. And it is absolutely important to think about that in the context of the growth regression. It's a good thing to think about. It's a good thing to think about. I think, it's a good thing to think about. Absolutely. And then you were saying about the independence assumption. Yeah. So that's you can allow for some relaxation in that. There's recent work on doing this with clustered data and some good progress on that by Sasaki and students and others. So there's some, but it does rely on some independence assumption somewhere for sure. I'm getting a little, so that's particularly the cross fitting I'm thinking about. Yeah, but cross validation does rely on independence. Definitely.
Thank you
Good
again.
point.
Thanks.
Yeah, sure.
I know that Whitney has to rush at 11. Just very quickly, so there's a team of former students in China where we've applied the automated version of this to deep learning and optimal portfolio. Ran horse races with farmers, farmer French 3 and 5 factor models. We pick like more than 19 factors. So, a little bit of relief in terms of what functional form, no longer linear, and a little bit of relief in terms of how many factors we consider. And the results look pretty supportive. Sure, like anything else, it's not a cure-all, but it is nice to have more freedom in terms of what kind of non-linearities and machine learners and how many variables and polynomials of these variables and nonlinear functions of these variables one could use, and making sure that one doesn't fall victim to the biases because of over focus on prediction is nice, is a nice way of thinking about extensions of this. I'm sure there are plenty of other good comments and questions, but we've agreed to let Whitney rush to his other burdens and
I can answer one more.
Sure, go ahead. Any other questions?
Said, go ahead.
One more. Saeed had his hand up.
Yeah, I had a question about this P over. Do you hear me?
Yes.
I had a question about this P over N. In big data, I imagine P over N should be quite small. It's true that we have a lot of covariates, but compared to size of the data N, P over N should be quite small, as opposed to the example of convergence you showed us, P over 90 countries, only 60 covariates.
Yeah.
So in large data or big data, P over N should be quite small. I was wondering whether this approach will would be more advantageous compared to least square.
So one thing just about lasso, the P can actually grow much faster than the sample size. The key thing that makes that work is the you have to, in order for this to be useful, you have to have that this P can be very large, much bigger than the sample size, and the theory for a good convergence rate for lasso still worked. But you need approximates probably. So, which is said, there has to be some reordering of the coefficients so that they decline at some. That got that. You actually, you can be large, and you don't need. That was the hook that actually kind of helped me get interested in this. Is with lasso, you can have many regressors. You have to have a few of them that are important. You don't have to have sparsity. You don't have to have a lot of them being zero, but there's got to be a lot of small. and then you don't have to know which ones are important, and you can do lasso and it'll work well. Okay.
Whitney, thank you
That's
so
helpful.
much. We truly appreciate it. And I highly recommend the papers that you cited. We look forward to receiving and posting the copies of the slides, the presentation. That would be great.
Okay, I'll send the slides to you.
Thank you so much. Kamir has an announcement about the next IIEA meeting.
Thank you very much, Essie John. Thanks everyone for joining us. Thank you so much, Whitney. That was very interesting. Lots more questions, I'm sure, but appreciate your time. Our October webinar, the details of it will be posted on our website. Whitney's talk will go on the YouTube channel as usual in the next hour or so. And our October webinar is on Are Sanctions Gender Neutral? Insights from Iran and beyond. So we hope to see you there. Thanks, everyone. Thanks, Essie, for excellent sharing.
Thank you so much. Thanks. Cheers.
Bye.
Cheers.
Bye.
Bye-bye.
Bye-bye. Bye, Whitney.